today I would like to introduce kind of unique, maybe, way for how you can perform DFT calculation in really easy and trivial way. So in today's tutorial, we are not tackling more difficult or difficult terminology in terms of DFT calculation. Rather, we would like to orient you how you can perform DFT in a really easy way, of course, by using the MatSQ platform. So in my today's tutorial, I would like to focus mainly on three parts. The first one, I will discuss about what is actually DFT calculation by showing just brief introduction for the history of DFT calculation and how we finally deal with DFT calculation to our research in material science or chemistry, okay? The next one, I will talk about the input file. Input file, actually, this is kind of your script, how you can maybe discuss or translate your ideas or scientific information into the code. The code, how the code can understand what you want to do, okay? So the input, this is kind of your script and the connection point between you and the computer. Finally, how you can get specific calculation you want. Finally, I will go for the actual practice. So part C, this is where you will see how we can perform DFT calculation in a really easy and good way. And I am tackling here two problems, how you can calculate the adsorption energy, and the second one is density of state. Of course, there are really way, values and results you can evaluate and calculate with DFT calculation. I will show you how you can finally extract such kind of values and how you can learn it. Even I am showing just two examples today, because of course this is very short tutorial. We hopefully would finish this tutorial within hour or hour and a half, but I think within an hour we can finish the tutorial today. So in today's content, I will go what is actual DFT calculation, why we need to use DFT calculation, and the key concept and potential. Maybe you are not understanding anything now, but just follow me. So when we are actually discussing and talking about DFT calculation, we are in a way or another way, we are trying to solve something called Schrödinger equation. So Schrödinger equation, which is the first principle or ab initio method for electrons. So this kind of, ab initio calculation, there are different methods. There are really several methods trying to solve this kind of principle. But the main important or common methods, which known for really scientists, the first one called density functional theory or DFT. The second one called computational quantum chemistry. So maybe if you are a computational guy, or if you are into this field or trying to jump learning this field, you would hear a lot about density functional theory, computational quantum chemistry. And if you are reading some kind of paper, sometimes they say we are using ab initio calculation. And ab initio calculation nowadays, in a trivial way, it refers to either DFT calculation or quantum chemistry, okay? But what is actually the big difference between these two methods and why I am showing in here? Also, I am just going to discuss about DFT calculation, but I'm trying to show what is actually the difference between these methods for tackling the Schrödinger equation. It will really help you to understand what we are talking about, okay? So density functional theory, it actually cares about the density of electrons. So you are trying to calculate something called density of electron or electron density. It's very simple. So what is the density of electrons of your system? The method or equation using to calculate the electron density of your system, like carbon, iron, any kind of structure you are dealing with, metal or non-metallic material, it's called Kohn-Sham equation. This Kohn-Sham equation was developed by Walter Kohn, and it is really good to deal for or understanding or studying the solid material. It's really good for physics application and material science study and engineering. Okay. In the opposite way, computational quantum chemistry, it's actually trying to solve the wave function. So we are trying to calculate the wave function based on the Schrödinger equation. It's a really complicated method. This is why it suits only for molecules and in chemistry application, because it's really difficult to find system with very small interaction between electrons, because it's really heavy method. I am also showing here the main difference between the DFT calculation in terms of really important information. Of course, the theoretical information, if you are really would like to get a deep information about DFT, this is a really huge science. So there are really several classes and lectures we have already prepared. So if you are interested in this one, please contact me. I can maybe guide you how you can get the theoretical background about DFT calculation. So DFT is a quantum mechanical method. It used, again, to investigate something called electronic structure of many body systems. So it's about the electronic structure of the material. Instead of focusing about wave function, which the Schrödinger equation actually about, we are not interested about the wave function. DFT deals with the electron densities. So if you are able to understand or calculate the electron density of your system, by this way, you would understand the overall behavior of the material. Thus, you are reducing two things: the computational problem significantly in terms of time and efforts. So using DFT calculation, it actually gives you a kind of a practical way how you can solve Schrödinger equation. So DFT again relies on the quantum method. What kind of codes maybe using DFT calculation you have already, or maybe you didn't hear about some codes which mainly dealing the quantum equation or the DFT calculation. The very well-known or famous code called the Quantum Espresso. So Quantum Espresso, this is one code which actually applies the quantum equation to solve Schrödinger equation or the DFT calculation. We have also BASIT, we have SISTA, GPAW, CASTIP. However, I'm mentioning here several kind of codes, but most of these codes actually commercial codes and it's paid, so you need license, except Quantum Espresso. So Quantum Espresso is open source, is really good code. They have already a lot of potential that we can use, and they have strong scientific community. So you can update, ask question, and get what you want easily. And still, it's for free, so to use. I mean, the source code itself. I mean, DFT, again, it's really good for solid material. In the opposite way, quantum chemistry, in just trivial way, it mainly study the quantum level. It compasses the wide variety of methods, including Hartree-Fock method. This is mainly how you can calculate the wave function. So it's again not about electron density, it's calculated something called wave function. The famous code which dealing with computational quantum chemistry is Gaussian, ORCA, GAMS. GAMS is very famous because it's really good to studying the molecule itself. So you can get more deep understanding about the molecule if you are dealing only with single molecule, not about a bit larger structure. So it's really good for molecular system. But again, in today's tutorial, we are only caring about the density functional theory. So in very simple word, DFT is about how you calculate the density of electrons, not about the wave function. So this is the Schrödinger equation. It's really complicated. I'm not discussing for you, but I'm just showing in here if someone would be interested about the Planck constant, what is the wave function, the change in the wave function, and how these actually get together to form the Schrödinger equation. Okay, so let's get closer about why, for example, we needed to use DFT calculation, why we are not able to solve Schrödinger equation, why, for example, Schrödinger equation is really difficult matter to solve. Okay, so density functional theory, again, is a quantum mechanical method used to study molecular and solid state electronic system. This is how we define the DFT. So the core idea, again, instead of solving the complex many-body Schrödinger equation directly, DFT focuses on the electron density as the primary variable. So because the density of electron, once you evaluate, you can gain a lot of information about the structure. So you can understand the characteristic, the energy, etc. And then you can relate what is the behavior of this material. But again, why it's really hard to solve Schrodinger equation. Schrodinger equation can be really possible if you are only dealing with single atom like hydrogen, because hydrogen has only one electron and one proton, okay? So we have only one electron and one proton in single hydrogen atom. So every electron or every proton, they have three coordinates. We have X, we have Y, we have Z, okay? So X, Y, Z for the electron, and we have X, Y, Z for the proton. Then we have 6 coordinates. So 2X, 2Y, 2Z. Then, because we have 6 coordinates, this is called freedom. So we have kind of 6 degrees of freedom, like different possible of variation that would be resulted from these coordinates, okay? But if you have single oxygen in the opposite way, I mean, single oxygen would have 16 electrons. Just I'm trying to make it really simple. So 16 electron, each electron has 3 coordinates. Then how many degree of freedom we have? We have 48 DOF, okay? Degree of freedom. Maybe someone would tell me, okay, what's the difference between 6 and 48? They are still very small number. But in terms of Schrodinger equation, this is really a big deal. Okay. I'm trying to make it simple for you. If you are looking to this only electron, okay? This is only electron. This electron, if it's really isolated, if we are putting this electron in single room, this electron doesn't have any interaction with the surroundings, okay? So we don't have to worry about any other probabilities. I am sure this electron have no interaction. Then there is only one probabilities. If I put 2 electrons, okay? If I put this electron with this electron, then they would be interacting with each other. How about if I add one more electron? Then I would have this interaction with this interaction with this, and this interaction with it. How about if I put one more? Then it's getting really complex. To make it really simple for you, I usually use this analogy. Suppose we have a student, her name Dora, okay? Dora, she is sitting in her school alone. There is really no chance for Dora to be interacting with other students, or maybe making problems, or fighting, or giving her pen to her friends, or trying to eat together, or going for lunch together, or playing a ball, or refusing to play the ball. Then all of these probabilities is absent because we have only one child or one student in this school. How about if I put all of those students together? Dora, maybe she will have chance to play with student A. Maybe she doesn't prefer to play with student B, but student B would have chance to play maybe with student A, while student B would fight with student C. Maybe they goes together in a team, but they are not planning to play with Dora. So this is really kind of the story of Schrodinger equation. So Schrodinger equation, it aims to understand what is the movement for each student of this one, what they are actually doing, what is the activity of these students, okay? So this is mainly what Schrodinger equation aims to do. While the DFT calculation, it just interested about what is the condition or what is the status of the whole school. Maybe this school is really noisy, it's calm, it's active or not. By this way, I can understand if I am saying the overall status of my school or my classroom, it's active or noisy, then the student, they are interacting with each other. So it's really complex to deal if we are really tackling each student, what he is doing. So this is simply what we are mentioning. Then if we are dealing with Schrodinger equation, this is really complex equation. Again, in Schrodinger equation, complexity, this is very important. Complexity doesn't add up. So when we are adding one more electron, we are not simply a plus equation. We are not doing the summation in mathematics. We are trying actually to multiply, because each electron would be interacting with all other electrons. So this is why it's really complicated. In DFT, we don't care about the quantum state system, but we care about, and we aim to find the electron density of the system. Again, this is how we can refer to the classroom if it's noisy or not. Okay. Again, then DFT is one way or one method to solve Schrodinger equation in really trivial way by using some kind of approximation. I'm not going for technical, just to make it really simple for you. Once we try to go to the site and performing the real DFT calculation, you can understand and grasp what each terminology would be shown meaning, okay? So then why we need actually to use DFT? It's very good, I mean, important properties for DFT that allows really researcher to jump and doing DFT. Maybe it's become really good and common nowadays because, of course, the supercomputer, the high-performance computer, cloud computers really become more affordable. And this is why nowadays you can easily build or maybe access any cloud computer resources and run your DFT calculation. So DFT provide really good balance between computational efficiency and accuracy. Again, because Schrodinger equation is really difficult and complicated to solve, DFT can give you alternative of understanding and solving the Schrodinger equation in really good way. So you can understand and get kind of prediction what's actually going on in your system. Flexibility, it can be applied in really wide range of systems. Almost all kind of systems, any kind of system or materials, you can deal with DFT calculation. There is really application. Always there is application where you can use DFT calculation. It's really cost effective in terms of computational cost, other than quantum mechanical, again, because quantum mechanical, they are aiming to evaluate the wave function, like Hartree-Fock, where approximate the wave function of multi-electron system by considering electron-electron interaction in average manner, or post-Hartree, which include the electron correlation missed in the Hartree-Fock method. This is not, I mean, important information to know, but just get introduced to this kind of method that being used with DFT or quantum mechanical method. In the opposite, DFT working directly with many electron wave function. I mean, it doesn't work like Hartree or many wave function. It works with the electron density. So it's very simple entity we are dealing with. Density is very simple quantity compared to the other values in quantum mechanics. If I am comparing DFT with other code, maybe you have already heard about something called molecular dynamic simulation, okay? So maybe now you are saying, okay, what is the difference between molecular dynamic simulation and DFT calculation? DFT calculation, it really cares about electron, while molecular dynamic simulation, it cares about the particle. So molecular dynamic simulation, it deals each atom as a solid particle. So there are really several potential models which can included the maybe density interaction or density properties or charge density with their potential model, but it kind of balls interaction and collided with each other. So in terms of fact, like the electron interaction, when you are actually caring and understanding the electrons interaction of the atoms, then you can get more deep and more accurate understanding for your structure. This is why DFT is much accurate, more accurate than molecular dynamic simulation. Also, maybe some molecular dynamic simulation can be really good if you develop really strong potential model, either using machine learning or really strong data experimental with DFT. However, still MD, they are also having different applications, especially if you are dealing with larger structure like thousands, hundreds of thousands of atoms. But DFT can be only limited with very small number of atoms because you are interested about the atomistic properties of the material. You are really in early stage. If you are achieving the fact from the basic science of your structure, then you can understand and you can develop a new material. So it's very important for developing novel materials and new material. Okay, where we can use DFT. DFT almost has application in almost every science we are, we introduced to know. So in nanoscience, they have application in chemistry, they have application in biology, they have application in physics. So I'm just giving here an example so you can relate from your different background. Like I think we have now many attendants today, so I expect many of them would be from biology section or from physics, chemistry, material science. So you can relate actually. So in biochemistry, for example, how you can use DFT, you can understand how enzyme, substrate interaction or drug binding affinities, okay? It's really good in also the drug exploration. Surface science, you can investigate the absorption of molecules on metal surface. Why maybe you would say absorption is really important on the surface? Because absorption, like strong absorption, it can show you the nature of interaction with the surface. So this is kind of catalyst, maybe it could be a catalyst application. So you can design new and novel materials, either nanoparticle, surface material, can be really good for specific synthesis reaction, for hydrogen production, ammonia synthesis, water splitting, etc. Any kind of synthesis reaction. It's really good for also batteries. There are really thousands of papers. I remember it was published really in very short period of time, only by using DFT calculation for the batteries and semiconductors. So DFT calculation can allow you to study the ion migration in battery electrodes to improve energy storage. So nowadays, maybe you have heard about the revolution of electric cars, Tesla. It's really strongly based on the devolved material like lithium batteries. Nowadays, maybe you have heard about sodium batteries or other kind of new batteries which targeted to replace the electrodes or anodes of different materials. All of that has been done and achieved with the power of DFT calculation. Of course, you need to approve and confirm with the experimental next step, but the initial step has to be with DFT, especially with the novel material, like the new material that you are aiming to expect or explore. In the memory system, you can explore the magnetic or ferromagnetic properties essential for memory device. In terms of mechanical characteristic, you can predicting also the strength and elasticity of new materials. Photonics, designing material with specific optical properties for telecommunication or imaging. This is also very strong and important topics in the current era of our technology, because designing new photonic materials with really specific optical properties is very essential to keep actually adapted with the current huge development, especially in the machine learning and AI application and tech robotics, etc. So still, what is actually the strength and weakness of DFT? So I'm not saying like DFT is really the magic tools. It would, the magic tool, which is the only, offered for scientists. But it has really strong point where we can use, and it has also weak point. Maybe it's really not good enough to be used, but it still can be applied. So it's really good for density of state. It can accurately describe the electronic state distribution over energy. It's really good for structure determination. It can also predict the equilibrium geometries and atomic arrangement effectively. It has really good also for vibrational frequencies, good for predicting vibrational mode or of molecules and material. But it is also well known that DFT cannot be good enough for band gap calculation. I will just mention you maybe LDA, GGA. Maybe if you are not into this field, it can be really difficult to understand now. But in the next slide, I'm just in trivial way showing what is these LDA and GGA actually in DFT. Dispersion interaction, strongly correlated system like with system where electron-electron interaction is really strong, especially for transition metal oxide, DFT maybe cannot be good enough, but still it has really way different application where you can use it strongly. I am saying here like PAW, LDA, GGA, just again to keep you adapted and familiar with this terminology, because when I jump to the Material Square platform, maybe you will see this kind of terminology, then you would understand what I'm talking about, okay? So PAW, or projected augmented wave. What is this one? Actually, this one describes the treatment of electron-ion interaction in DFT. Because again, each single atom, it has two parts, electron and ion, okay? So if we have electron-electron interaction, then how about the electron-ion interaction? This can be treated with the PAW, projected augmented wave. So the purpose in this one is a method to efficiently handle the electronic structure near atomic cores, combining the accuracy of all electron calculation with the efficiency of the pseudo-potential. Pseudo-potential, this is kind of, how to say, this is kind of, maybe we can describe the structure of the materials. So each maybe atom or each different material has specific pseudo-potential, and pseudo-potential can be suitable for different kind of application. However, we have also theoretical lecture where we describe detailed what is the pseudo potential actually is. LDA, or local density approximation, and GGA, generalized gradient approximation. What actually are these LDA and GGA? Maybe you will see a lot in DFT, or if you are reading a paper, they have the methodology section, they would say like we are using LDA, GGA, or they are using POW, something. So LDA or GGA, it describes the treatment of electron-electron interaction. Again, all of these I am mentioning in here, I mean, this approximation is mainly the way or support solving the DFT calculation as whole result, okay? So solving the DFT calculation, it has a lot of approximation inside. And what I'm showing in here, this is kind of approximation. It's actually dealing each case, or it has a specific application where we actually need to apply. So the purpose, the exact form of the exchange correlation energy is not known, while LDA and GGA are two different approximations to tackle this problem. So LDA considers the electron density as a point. So it assumes, so if like some material, they would say we're using LDA. Other material, they say we're using GGA. Why? Because each kind of calculation would actually affect which kind of approximation you need to use, LDA or GGA. This is based on the scientist experience. Maybe they have approved this will be really good, and this would be maybe a little bit weak, okay? So LDA assumes that the electron density at a point in space and uses a uniform electron gas approximation to estimate the exchange correlation energy. In the opposite way, GGA improves the LDA, because initially it was developed for LDA. It's kind of an improvement for the LDA by considering not only the electron density, but also its gradient, like how the density varies in space. This often provides a more accurate description for many body system. Okay, now let's go for the actual, I mean, the real application of the DFT calculation. Okay, I am just already presented the DFT calculation in the theoretical background. Of course, it's really nothing to deal with details or technical terminology in here, but I'm just trying to show you a really trivial understanding what is the DFT. So the summary of the first part, that DFT calculation, this is a way of solving Schrodinger equation by considering the electron density, right? So we are dealing about how we can solve the electron density of the structure. By knowing the electron density, you can understand a lot of information about your structure. And we have a lot of approximation side like LDA, GGA, all of that belong to the DFT calculation. The first thing I am talking about, again, we are, I mean, in our tutorial, today's of DFT calculation will only present Quantum Espresso. So Quantum Espresso, this is the solely code that is adapted and integrated in our platform, in Material Square platform, okay? So we are not discussing about other codes. Of course, there are really many other codes, but the well-known, the really good reputation, and it has also, I mean, it's a free license code, so you don't need to pay to use it, okay? So this is open source, and it has a really strong community, and always there are really a good development and application from time to time. So it's really good for any scientist to start with Quantum Espresso. The most important thing in a Quantum Espresso is something called input file. So what is the input file? Input file, this is kind of tools, again, tools or script. How, like if you are a researcher, just maybe you can remember, this is you are a researcher, how you can send your ideas into the computer. Suppose this is computer. How you can tell the computer to calculate maybe the absorption energy, density of state, or any kind of calculation. To deal with this fact, actually, this kind of protocol known as input file. So input file, this is kind of script, can talk to your computer and discuss with, transfer your information or your needs of calculation into a language or into a tags, finally, the Quantum Espresso or the DFT code understand, okay? It's just take it one by one. But in general, what actually what is, the actual process when we are saying DFT. What's going on with DFT? Okay, I'm just showing you, this is kind of the scheme, how the DFT calculation actually starts and goes. The first one, we have the general approach of DFT going this way. So this one, when we are starting the DFT calculation, at the first we are starting something called the convergence test. So there is kind of actually parameters like K point, okay, and energy cutoff. I will show you in the material square where actually these K point and energy cutoff. So it will be really more easy for you to understand. But these kind of values, you have to assure it is suitable for your structure. So this is what we call convergence test. For example, if I am increasing the K point as much as I want, and maybe I'm increasing the energy cutoff as much as I want, of course, this is really good, maybe, especially for the K point. When you increase the K point, the accuracy increases. But at the same time, the calculation cost would be really extremely increased. So it will be very costly calculation. So you have to find kind of balance. So trade-off balance between the energy cutoff, K point, by following the convergence test. So you have to do this one. Conducting a convergence test for the energy cutoff mean increasing these cutoff values and performing the calculation at each step. So by doing this way, you actually identify the minimum cutoff value. So we can reach where is the minimum cutoff energy or the minimum calculation settings would be really prepared enough for my calculation, such as maybe you are doing total energy, you are doing you are trying to deal with atomic forces, band structure. These values would be converged to a stable values. Finally, you can conclude your K point and energy cutoff. This is kind of calculation setting, okay? So maybe some of you would say, what is the K point actually, okay? In DFT or Quantum Espresso, in general, K points actually are the points in reciprocal space or Brillouin zone, used to numerically integrate the electronic state. Maybe if you are in physics or even material science, you would understand what is the reciprocal place or Brillouin zone. So it's mainly used to numerically integrate the electronic state. Conducting a convergence test with the K point involves increasing the density of the K point grid until your properties of interest converge. So once the convergence is done, so after this step is actually done, we have to do something called, this is structure relaxation, but finally we have to do something called SCF calculation, self-consistent field calculation. This is very common. So if someone has been already getting into the tutorial of DFT calculation, maybe he has heard a lot. We will do SCF calculation. SCF calculation. What is actually SCF calculation? This is used to solve the Kohn-Sham equation iteratively. So there is kind of iteration process going on to solve DFT calculation. So SCF calculation is where you actually doing the solution for the Kohn-Sham equation or the DFT calculation. And SCF calculation, this is kind of really kind of a start for so many of the calculation we are doing in DFT. So every DFT calculation mainly would be starting with SCF calculation. This is kind of basic calculation you have to do for each time, okay? So this is what actually going on when you are trying to run the DFT calculation. Finally, after you are doing SCF calculation, you can get a lot of physical properties like band, optical energy, absorption energy, etc., etc. Okay, now let's deal what is inside the input calculation. What actually the input, the input file in a Quantum Espresso it has. The first thing, we have something called the name list. This is the main three name lists, okay? We have control, system, electron. So if you open the input file in a Quantum Espresso, you would see this one, this at and control, and it will be followed with several lines. Then the second one, it will be system, it will be followed with several lines, electron, etc., etc. I will also discuss about each section, then you can understand. So why we have to follow this kind of arrangement? It's you are writing a paper. If you are writing a paper or you are writing an article, you would start with this kind of arrangement. You will start with introduction, you will introduce paragraph 1, paragraph 2, paragraph 3, 4, etc., until you reach to the summary. This is what make your actually article an article. And this is again what makes your input file an input file of Quantum Espresso. You have to do and follow this kind of arrangement. Okay. So this one, what we call it with name list. So this is the name list where you can define several of options and properties of your structure and what kind of calculation you are really aiming to do. After you finish each name list, it has to end with closing tag. So when you put this one at the end of here, like I wrote at control, I wrote line 1, line 2, line 2, line 3, and I did this one, it means the control section is done. Everything before this closing tag is belong to the control. Everything after this tag, it belongs to the next name list, okay? So starting with the control, this is how it will be written. So we will write control. We have to introduce something called name card 1, name card 2, etc., etc. What actually these name card 1 and name card 2? Let's just give you an actual example. So this is taken from real input file of the Quantum Espresso. So this is real input file of Quantum Espresso. This one, again, this is at control, the same, the first name list. We define the general variable and most important controllers to run. Always I'm saying this kind of control, it's actually like administrator to the process. It's control the process. So it defines some of these name card and I mean, each name card, it has specific task and job during your calculation. So I am saying here like calculation defining to be SCF. Again, I say like SCF is the main calculation that we are doing with DFT calculation. SCF is mainly about solving the Kohn-Sham equation or solving the DFT calculation by iteration process. So it's iterative process. However, we have different type of calculation, not only SCF calculation. We have SCF and SCF, bands, relax, V-relax, MD, VMD. There are really a lot. I will show you also how you can extract all of these options and how you can decide, okay? So SCF, self-consistent field calculation, and SCF, non-self-consistent field calculation. This is really important when you are doing like density of state calculation. Relax, this one. This actually keeps the cell fixed. When you are applying relax into your structure, you keep the cell fixed. Only the atomic position actually changing. So we are considering only the atomic position to be changed during the optimization. While when we are saying BC relax, both, we are doing relaxation for the atom of the structure, and we are doing the structure, I mean, the box itself would be relaxing. MD, this is for a mixed calculation, actually, molecular dynamic calculation or also mixed calculation. So I'm showing here, but before I'm going to the platform at the end of this, while I'm introducing the input file, I will show you how you can actually extract these kind of information from the manual itself, the Quantum Espresso manual. Next one, this one kind of pseudo-potential directory. Pseudo-potential, again, this is very important. You can define what is the location, where is the directory of your pseudo-potential. Only you can say maybe C something, or if you are working in your server, you can define this one, or just default. So if you put dot, it will be the default value in your current directory. So if I put dot in here, it means like I mean, the current directory I'm working on, it will be where is my pseudo-potential is stored, okay? Go to the next. There are different kind of name cards, not only calculation or pseudo directory. We have also, we have prefix, out, dir, etc., etc. Each of these name card has their own, I mean, application and own needs, but I'm just only showing you the simple one for the sake of understanding and explaining. It's really in really simple way. I don't want to make it really complex until we go directly to the application, because the main target of today's tutorial is to give you really easy way how you can just run and perform DFT calculation without caring about compilation or coding, etc., and more technical problems we have. The next one, the next name list, it's the system. So again, you are writing at system, and you can introduce the name card 1, name card 2, etc., in the similar way as to the previous control. So in system, we are providing input variable to the system we want to study. So we define, for example, the Pravis lattice we are using. To each Pravis lattice in here, one particular number is assigned. For example, when we are saying iPrav equal 1, it's not always 2 actually. It could be 1, 2, 3, up to 14. This 1 means our lattice is cubic, and code understand this way. 0, it means free, that we don't know what actually our structure is. If we put 2, it means FCC. Okay, so this one means FCC structure. If we put 3, it means BCC. If we put 4, it means HCP structure, etc., etc. We have 14 different structures. Okay, this one I will show you also on the manual itself what actually each number really means. The cell dimension, cell DM1, this is used in combination with the atomic position. Like this one sometimes would be in combination with the atomic position together with the cell dimension. So if I'm defining cell dimension, maybe I don't need to define here, but if I'm not defining, I need to define what is my cell dimension here. So cell parameter or cell dimension, it's used to define the geometry of your system, while the atomic position in here actually describe the crystallographic cell vectors. What is the XYZ of your atom? So cell dimension 1, this is used to define the length scale of the crystal cell I have. It sets the lattice constant, and it used to scale the lattice vector. So when we are saying cell dimension 1, actually, we are using the scale to the cell parameter, okay? Which is turned to define the lattice from the atomic position. So all of this information will be introduced from the atomic position. It will be included in here. So all of these 3 parts work together to fully specify the crystal structure for the DFT calculation. While again, 11 in here, it means the unit in core radii, okay, which is about 5.8 angstrom. We have, again, we have also several values of this one. It could be like 2, 6, and it can be also defined to the shape of the cell. For example, if we are saying cell DM2, this one, and cell DM3, this is the ratio between the second and first, or third and first lattice vector respectively. While we have also cell dimension 4, with cell dimension 5, 6. This is give also the cosine and the angle between the lattice vector. Okay, maybe you don't need actually to understand all of these values. Again, when you are trying to get introduced to the material square platform, all of these values would be default for you. So we have kind of the default form will be introduced for you. Okay, the next one, we have the number of atoms in supercell. NAT, it's mean number of atoms. We have 2 atoms in here. And type, the next one, it means how many types of atom we have. If I'm saying I am only studying the pure iron, then we only have 1 atom type. If I'm saying I'm studying the water, we have 2 atom types. So the number would be 2 if I'm studying the H2O, for example. Okay. The next one, this is ECUT W FC. This is how broad of function will be. Okay, this is energy cutoff wave function in this unit. While we have also the energy cutoff rho, ECUT rho, I mean energy cut of density. Usually these values actually are correlated. So if this one is 20, this value usually 6 to 10 times of this value. So if, for example, we can get this one from the potential model, I will show you also how you can extract this value. And this value can be 6 times of this value or 10 times, it depends on the material we are dealing with. So for example, in metal, even this material could be 12 times, I mean, the best result, while the average range has to be from 6 to 10. However, these two parameters, they are related, and also they are correlated with the K points itself. Okay. Okay. I will not go really deep too much about the input file because I have explained in details. Just let's go in a bit faster, and maybe the most important to go to the platform itself. So we have also the smearing value. We have different kind of smearing, like we have Gaussian, Smith-Bissell, Paxton, Marzari, Vanderbilt. We have also Fermi-Dirac. So these kind of smearing, it has really their own application. Maybe Gaussian, actually, it works maybe for the most cases, especially for the metallic system, while this one, maybe Smith-Bissell, Paxton, it could be a really sophisticated method, but it has really better result in general cases. It's really good for system with small or zero band gap. So you can understand now why there are really several smearing methods. While Marzari, Vanderbilt, this one, it's good for estimating like the free energies at low temperature. The last one would be really good for simulation at finite temperature. I think I have to go to the electron. Electron, similar way, we are defining the electron maximum step. So the default value, this is the maximum number of iterations. Again, I'm saying when we are doing SCF calculation, we are doing iterative process. So there would be iteration process going on to reach the convergence. While the default value is 100 for this one, if you are put 200 is better because the quantum espresso will be terminated if we are maybe using lower values. So the conventional default is 100, while the recommended value, especially if you are doing VC relax or relax calculation, to be 200. Okay. Convergence threshold, it means actually if my calculation or the iterated result, the difference between the current iterated value and the next iterated value is 0.0001, it means the accuracy is achieved. Then the calculation stops. We have also this one, I mean, starting potential atomic. It means that the code will take the superposition of atomic charge as a starting potential. Atomic, it means this option typically used when we have no previous result. So if I am already done the first SCF calculation, I will have this kind of file. So I can use this file by starting another calculation to save the calculation time and to get better accuracy. However, what kind of content would this file have? This file where the electronic charge density from previous calculation is stored actually. And the charge density is a key result of our SCF calculation. It represents the distribution of electronic charge in our system. The next one is the K point. This is also very important value. We provide coordinates and weight of the K points, which will be used in the Brilliant zone integration. We have maybe two main things like this one. So the common one is automatic, okay? And we are here set the sampling of the Brilliant zone. There are there are three sampling methods used in the K point, like Moncourse back scheme. We have gamma point calculation. This one often used, okay, I think, okay. So this one is often used for calculation that require integration over the Brilliant zone, such as density of state or band structure calculation. I mean this one, okay. The next one, it's simplest form of the K point sampling, where only the gamma point K equals 0 is used. This method, again, is fast, but only suitable for system with high symmetry. So this is with high symmetry system. This is when you are aiming to calculate density of state or band calculation. The third method, I think this one, I don't know if I shall discuss for you because it's not common and we are not using a lot, but this is kind of high symmetry, okay, high symmetry point, and usually this is the default value. If you have defining this value, it means you are defining the high symmetry K point in the brilliant zone. This method often used for band structure calculation, while the K point path, I mean, the style of the K point is defined along the high symmetric direction in the brilliant zone. So, for example, you have these all in the brilliant zone, gamma, x, and gamma. We have 8 values, okay? So each value is defined in this way, 0, 0, 0, okay? While this value, it tells like Quantum Espresso to compute the electronic structure at gamma point, for example, in the gamma point, the origin of the brilliant zone in the reciprocal place, and that 10 state at this K point will be calculated. So this is kind of numbers. If you are moving to the X value, 10 again state will be commuted at this K point. So this is number of state where at each part of the brilliant zone will be calculated. Maybe you don't need actually to go deep this time because we will move to the application soon of where we can do the DFT calculation. Atom species again, we will provide here like the name, the mass, pseudo potential used for each atomic species in our system. The atomic position, this is how it looks like. Maybe if you have been introduced to, for example, the postcard, maybe you can see there is the atom. What is the atom in my structure? And this is the coordinates of my structure. It has been crystal, atomic position, information. It can be introduced in here. Okay, so soon I will go to the platform, but I will tell you something actually. What is the unique of today's tutorial? I didn't mention how, for example, how you can install the DFT code in your platform or in your machine. What kind of codes you need to learn, what is the HCP computer, what is the bashing environment, what is the Linux. This is really kind of barriers, okay? This is why many researchers in the world cannot actually jump or adapt to the DFT calculation because there are a lot of barriers. And in today's tutorial, I will show you how we can withstand, bypass these kind of barriers by just jumping to the Material Square platform. This Material Square, and this is how it looks like when you are trying to perform kind of DFT calculation. I will just join, I will connect to the platform itself to show you how we can practice, okay? So the first thing we will do today, okay, we will do the adsorption energy. I will show you how we can do adsorption energy soon, because adsorption energy is fundamental aspect of understanding the interaction between adsorbate species and the adsorbent surface. This interaction is crucial in various fields such as crystal, surface science, material science, environmental science. Simply, you need to calculate the energy of this structure, the energy of this structure, the energy of this structure. The difference between all of this energy, we can get the adsorption energy of this atom on this structure, okay? This is simply what is the adsorption energy. More negative energy, it's mean really strong. This one corresponds to the stronger adsorption energy. It means there is strong interaction between the surface and this material. So my example will be, let's jump to the platform. Okay, please just stay with me. I'll try to connect to the platform now. I think now you can see the platform, www.materialsquare.com. I hope everyone has already created his account. If you didn't, please just go now. I think in a few minutes, even with Google account, you can log in to this platform. I hope that you can practice with me. So this is when you put www.materialsquare.com, you can see this kind of window. Just go for start simulation now in here. You will see again another window where you can start your work, okay? So the first one I'm doing is the adsorption energy. So adsorption energy, I have already calculated this values. However, I will be sharing all of these data for you so you can check again and practice by yourself and do it again. So I will make two windows, the window which the calculation I have already done, and another window where I will show you each step how I have done, okay? So this window here, I will create a new window, new work. So now what we are doing, we are trying to perform real DFT calculation for our structure by calculating something called the adsorption energy. This, the workstation for you, I will go for the database. My structure was aluminum, okay? I will type here aluminum, I just search. You would see a lot of unit cell. I don't need to take any unit cell. I will just take this one simply. I think I picked this one in my previous case, how to check this one. Let's see in here. So this is my structure builder. It was MP134, okay? This is my unit cell. The first step, we have to do SCF calculation. I have assumed my structure is bulk. We have to do full VC relax. Maybe I have shown you this one, okay? So the really good thing in material square that you don't need to do anything by your hand. It's already formatted in really user-friendly interface. You just need to select and tick. Okay. Just for you to keep follow up with me, in the left window, the window in here, this the window where the calculation has been already done previously. And in here, I will just try to show you how I have performed these calculations. Okay, the first one we have done DFT calculation, and the structure was bulk. We have done full structure optimization with ion optimization. We have choose the spin polarization. This is energy cut was 30, 180. I didn't change because the purpose in this simulation, not very high accurate result, but just to show you the calculation, okay? So I will go for simulation, Quantum Espresso, general. You need to connect your structure. So, okay, I will connect my structure. Now, I have already connected my unit cell, the single aluminum atom of my structure with the DFT calculation. So you will do high accuracy. It has to be bulk. We have to do full structure optimization, ionic and cell optimization. You just select spin polarization. Okay, again, we have now doing energy. We are not doing any other kind of calculation. We are just keep the default value, energy, high accuracy. We are trying to optimize our unit cell, which is bulk, full optimization, ionic, and cell, it's mean the structure, and atomic position. We have selected the spin polarization, okay? This is K point also shown for you by default. This is K point. Maybe I showed you like the gamma high symmetry point. No, just keep it the default value. This is here 30, 180. But if you are really interested to get more higher accurate result, how I will show you how you can decide this value. You just go in here. Still, you can see actually the manual, the values, the input file in here. You can copy, paste if you want, but you just go for potential. You will see that already this potential has been selected for you. Just go for in here. I'm doing a step. This is not mandatory, but I'm just trying to show you how you can select this value. So it's suggested that for the wave function, cutoff energy has to be at least 29, okay? So if I assume this value to be 30, this is really good. So 6 times of this value, we have 180. So the default value is really good enough. So then you just try it in here. We will do maybe aluminum bulk optimization. However, everything I'm showing in here is for open source. This is a free calculation. But once you need to secure kind of a cloud server, then you need actually to have it. I mean, you have to select the package it would be suitable for your calculation or your academic research. This is kind of a service you need to check on the platform, but I show you how you can do this one. So this is the number of node also again selected by default for you. Just submit your job. So once your job is submitted, you will see in the bar in here. So you will see that your calculation is submitted and it's under preparation and you just need to wait. However, I have already done this calculation and in green color, it's mean already done and it has been calculated. So the next step, what we will do actually, I have to call the final structure calculation, okay? So how I have to calculate and call the final structure calculation. Again, because the calculation is not yet done here and would take time because this is the DFT calculation, I will show you. I will make another modeling, which is structure builder, okay? Structure builder in here. So what you will do module. I will connect the first Quantum Espresso, this one. Just call for me the final structure. So the final structure after the optimization SCF calculation has been called. The next step, what we will do, change your structure into conventional method. You will see a unit cell with 4 aluminum atoms, okay? Now I have to clone my structure. I have to enlarge my structure. So you will do clone. I think it was, how many atoms in here? Let's just see. I think it was 48 atoms, right? So we have to make it like, okay, 2 by 2, I think. Okay, 48. So we have 48 atoms structure of aluminum, which is my current structure. The next step is I have to introduce the vacuum. So we have to introduce the vacuum to my structure. The vacuum has to be in the Z direction with 15 angstrom. So you have this structure, okay, this surface, which is 0, 0, 1 of aluminum surface. You can actually play and change the, the atom. You can increase this way. You can introduce also bond if you want. You can change perspective. You can still also change the color if you want. So maybe you don't like this color, you can change this color or any color you want. Okay. Now we have to also again optimize this structure. However, this kind of calculation I have already done. I have already done it here. So after I finish the bulk structure optimization, I have finished this one, conventional, clone, vacuum, and we have done actually slightly move atoms. So just for the periodic appearance, to get better visualization after the optimization. The next step we have to do to optimize this structure, to do again the SCF calculation, but it has to be for isolate system, okay? It will be also done for ionic and cell optimization, spin polarization. It has to be also for K points, default value was 4, 4, 1, 30, 180. How to do this one? I will show you in here. So this is my structure I have built. You just go for simulation, Quantum Espresso, general. You have to connect your structure in here. Again, high. You have to do isolate system because this is surface. You will do ionic and cell optimization, spin polarization. The default value is 441, 380, and this is aluminum 001 surface optimization, okay? Everything is default, just submit. Now we have 2 calculations to be done. The first one, which is the single, atom, which is the bulk. After the bulk is optimized, we have to create the surface. After the surface is created, we have to do also the DFT calculation and relaxation for this structure. The next one, we have to create single oxygen atom. I have already created this one in my previous calculation. So this one, how we have to create this one? You have to call the single oxygen atom. Then you have to create a vacuum, place this atom in the center, and this is just kind of manual edit to place the atom in the center. And then what you will do Quantum Espresso. So this one, Quantum Espresso. It was defined as molecule with single atom and ionic optimization, spin polarization, everything is same, just to make the result is relatable. You cannot change you have to keep, it's really highly recommended to keep the calculation settings as a standard for you. So how we can do this one, I will show you again how we can create the single oxygen atom. Again, I am here in the right window just to show you some kind of calculation, how I can create. Oxygen. Okay, I have created this single atom. Then I have introduced the vacuum around. I created the box, so it has to be 5, 5, 5, 5, 5, 5. Okay, so I have this box, but the atom is not exactly placed in the center. So what I will do, I will go to the edit in here, and you will see your atom. It is actually, it's placed into the center. No, it's not exactly into the center. Maybe like draw molecule. Maybe this is O2. Just okay. Okay, done. Center of the box. Okay, so you have another way how you have created maybe single hydrogen. Maybe just select this one. So my point is there are really variety ways how you can create single oxygen or any single atom. This is exactly in the center. After you create this one, you just go simulation, Quantum Espresso, general, and you need also to connect your single atom this way, and high energy. It has to be molecule single atom. Okay. We have to also introduce spin polarization. So in this way, just show you the result, how it has been done. We don't need to just wait more. So the single oxygen was, so we have built the single oxygen, and then we applied the DFT calculation for the single oxygen, and we have kept the same default values, and we submitted the result. After that, we have achieved the optimization energy. So the next one, we have to copy paste. So you have to copy the single oxygen onto the top of aluminum surface, and you have to do again the similar DFT calculation. And this is how the DFT calculation is: isolate system, ionic optimization, spin polarization. But how you can copy and paste? How you can copy and paste your atom? It's actually really working very simple in our system. So you just go in here. So if this is my structure, you can, this one, select, Control C, okay, it's copied, and maybe you go for your surface in here, your surface, and Control V. Because it's connected with Zoom, I cannot. Okay. So it's the single oxygen. Okay, this one. Control C. Okay. Okay, so this is the single oxygen. Just you can use your mouse to bring it up. Actually, there is also very unique tools in MatSQ how you can control the atoms. not only this way, we have you can actually moving. So you just press S on your keyboard. Now S, I mean the selection mode is activated. So just select this atom. You will see this way. So if you select this way, you can actually move near to any atom you want easily with just moving the mouse. So maybe if you place the single oxygen in the top of the structure, then after that you need to do full optimization of our structure by submitting another DFT calculation where the oxygen is adsorbed to the surface. So we have three systems. We have actually performed the DFT calculation with the single oxygen atom. Okay, we have also the structure where the single oxygen atom adsorbed to the surface, and we have also the pure surface, the structure without any adsorption. So after the calculation is done, each of these calculations done, we will grab the energy. So how you can grab all of this energy? We have post calculation for the DFT calculation, I mean post code analysis code. So Quantum Espresso energy, I will connect this one and just now connect the other modules. I will connect this one, pure surface, with okay, another one. Okay, we have also this one. Okay, so we have three different surfaces: the single oxygen, the surface of aluminium, and aluminium where the oxygen was adsorbed to the surface. Finally, I just create this memo. How to create memo? Actually, you can do it in here, memo, and go for sheet. Okay, but I have already done in here. So from the energy values, I just copy. I put it in here. So we have the energy of the pure slab surface of aluminium. We have the energy of the single oxygen atom, and we have the energy of aluminium plus oxygen adsorbed to the surface. And just make the difference between all of this energy, you can get the adsorption energy of the single oxygen on the aluminium. Of course, this is not very accurate result, but this is how we can perform the adsorption energy calculation. I will not repeat what I have done for the next calculation, which is density of state. I will just show you actually, okay? Just go back, show you the calculation, because also I will share with you on the platform. So this is my work. We have the density of state, okay? So the density of state, I have created the graphene and I adsorb the single hydrogen, copper atom onto the surface and nickel atom onto the surface. And we have calculated the density of state and we shown what is the difference between these two structures. So at the first step, you can call actually this one from here. So you just go to preset. You can call graphene. We have hex in here. Okay, so now it's generated. But I have already done, so I just delete. So this one, then we will do clone. I created the clone by just going to the cell, clone the structure, make it 5, 5, 6, I think it was the number, and then this will be created. How you can add atom in here? I will repeat this step for you. So how we can add atom between these two selected carbon atoms. So you just press S, use your mouse to select this one. Now you have selected two atoms. Then I will go for the atom icon, add atom, select in here. I will add copper, okay? So center of the selected atoms applied. Now we have selected the single atom. Again, you can use C or A, select. I will select this one, okay, and just bring it up this way. So after you create your structure where the copper atom is adsorbed to the graphene structure, you need to do the DFT calculation for the structure. And the DFT calculation we have already done. After the adsorption energy is done, we have to do something called relax structure. So we have applied, SCF calculation with, again, high energy. The structure is isolate. It's mean the graphene where the copper is adsorbed to the surface. We have to do only ionic optimization. We don't care about the spin polarization this time. We have increased the value in here because copper and graphene, they need to have higher cutoff energy as compared to the previous structure, which was aluminium. And it will be 2, 2, 1 as a default value. And after that, I just submitted the task of this one. So after the calculation is done, then we will do the next step. The next step is the actual density of state calculation. Okay. So after this one is done, we will do something called NSCF calculation. Okay, NSCF calculation. I will show you how we can do this one. So just go one step to the previous one. It was, so this one, again, we have done the optimization, SCF calculation in this step, okay? So after that, we will just go for Quantum Espresso, general. You need to connect what? We need to connect the copper with the graphite, which is the first step of the DFT calculation. And this case, we need to choose density of state calculation, isolate, ionic structure. You have to increase this value to 50, maybe this one to 400, and the default value, and then you just submit the density of state calculation of graphite with copper. Okay, just save and start job. So when you submit your job, actually now you are performing the density of state calculation. Then how you can analyze this result? After this one is done, you just go for analyze, Quantum Espresso. We will do density of state. Okay, we have two modules. The first one is NSCF calculation, and it will be shown for you. So this is the density of state for the case of graphene, where the CO is adsorbed to the surface. We have also several options how you can control actually this graph. The good thing also in this graph, you can download. So the graph can be downloadable. So you can download in PNG, JPE, and other formats. So you can download. You can also change the color, and maybe we can change the style. Maybe we make it 3, empty or fill. This is you can play with. However, I have not only performed the density of state for the single atom in here, okay, I have also performed where the nickel was placed on the structure. So in here, I think, yes. So I have just repeated the same step, but I placed another nickel. So when we are comparing the two density of state in here, so this is density of state, I will connect this one with the result of, I think it was, yeah, let's just check. It was copper and nickel, yes, with the nickel. So we will have two density of state together, placed together. So we can see actually what is the difference between when the, okay, I just show. Just to make a difference better. So you can understand what is maybe the difference between placing different, adsorbent in the surface. Of course, it will change the electronic interaction between the graphene with the CO or Ni with the nickel. So this one, with DFT calculation, we can have a lot of understanding. Of course, this is it has really long discussion to talk about why, for example, it has this peak and it has sharpen here. It's closer to the Fermi energy, or it's a bit far from the Fermi energy. This is where you can correlate and understand the characteristic of the material. For today, I know it's very short tutorial, but I just really hope to bring for you a good tools where you can perform and run DFT calculation in an easy way. Because if you are new in this field, you couldn't maybe have faced the conventional or difficulties. Okay, if I'm showing you, so let's just go back to this slide. Okay, I will show you this slide. This one. Sorry. Okay, I will just mention something for you. Sorry, yeah, this one. So for anyone who would like to do DFT calculation, he has to actually pass a lot of barriers. The first barrier is you need expensive equipment, because when you try to perform DFT calculation, you need to have your own high performance computer, which is very expensive. Okay, but with Material Square, we are connecting the platform, which is integrating already all simulation tools, creating structure with DFT into the cloud. So you can run your calculation at any time you want from any place. You don't need to create your own server, you just run directly on the platform. The second barrier is the physical background. So in average, you need at least 1 year of understanding between the relation between computational physics, computational tools, and codes. Okay, how you can connect those different sectors from the theory and the simulation and the computer together. This is need a knowledge, and usually there are a lot of codes and package compilation process you have to achieve. Like in general way, if you are establishing your machine or high performance computer, you need to install a lot of package. Like you need to know how you can compile your maybe Quantum Espresso package, every method. There are also a lot of tools how you can perform DFT, density of state, band structure calculation, photonic calculation, IR Raman. All of these can be really easily done with Material Square. You just create your account, create your structure easily, and submit your task. We have also a bunch of tools. We have a lot of blogs, YouTube channel where we explain several calculations, how you can do with DFT calculation, Quantum Espresso, also molecular dynamic simulation as well. So if you search on YouTube Materials Square, you can still find a lot of examples in more deep problems and more analysis that you can achieve. The last barrier usually in the conventional, I'm talking here the conventional method of DFT calculation, is the complex Linux environment. Because when we are talking about DFT calculation, always comes that white and black screen to your minds, where you need to really write your script, like change directory, queue sub something, where you define the scheme of your simulation work. So it's not really trivial way, especially for someone from the experimental background. But with DFT in Quantum Espresso, with Material Square, this has become really an easy and trivial tool. I hope my today's presentation was easy. Maybe especially the last part, I really thought if I already prepare the material and calculate in a few days ahead, it could be a really good chance for you and could save your time also. However, I will share these materials. So if you are already creating your account, you can still access these materials and you see the calculation. Of course, this material already recorded, so you can come back again and watch. Still, if you have any question and problem, you can reach us into the question, assistant chat bot we have, where you can ask your question or technical question. We also organize one-to-one tutorial for anyone from really completely away background of the computational chemistry. We can arrange this one, so it can also tackle your specific case. So we have some people could guide you for your special case, and we can tell you what would be important and useful for you. Thank you for today and for joining me. I'm really happy that so many of you have already registered and joined my tutorial today.